All right, welcome to the second lecture in control systems. And today's presentation is entitled Mathematical Modeling, and this is the first of two parts. In this presentation, we are going to be looking at a principle called mathematical modeling. We look at the importance of mathematical modeling, types of models used in control systems, and we are going to look at how we derive the Laplace model. So, firstly, let us discuss the whole concept of mathematical modeling. So, mathematical modeling is deriving a mathematical equation that describes the relationship between the inputs and outputs of a system. Now, in a nutshell, what it does is to describe the system's behavior. So, when we speak of a model, sometimes perhaps we be much quicker to relate to models that are physical. So, for example, if there's to be a new development, let's say a new community development, the architect or the developers may present a model which is a scaled version of the development, and that will give persons who are stakeholders in the venture an opportunity to see what the expected outcome would look like. Now, in control systems, it's a little bit different in that when we speak of a system, any system at all whatsoever, and we could take, for example, let's leave engineering for a while in terms of example. Let's say we take the economic system, Jamaica's economy, as a system. Now, there are a number of inputs that go into this system. Whilst I'm not an economist, I'm not pretend to know all about that, but to keep it simple, we know that there are a number of things that will affect the growth of the economy. And so we could say the number of persons that are employed is one such variable. We could say that the size and number of disasters that occur in a year also affects the economy. And we could look at various other things that affect the economy. Now, the things that affect the economy, we could call them the input, all right? And the output, we could say, okay, how much did the economy grow as an output? Now, when we speak about a model, we are talking about a mathematical equation that describes the relationship between the inputs of the system and the output, right? So what that mathematical equation does is to describe the relationship between input and output. In other words, given the input, the mathematical equation can derive the output. So in terms of mathematical modeling, these models are derived from physical laws, all right? So if we're talking about mathematical models, physical systems, we may be looking at Newton's law, we may be looking at Hooke's law, and for circuits, we'll be looking at things like Kirchhoff's law and so on, all right? Now, what I'm saying here is that if you're going to derive a mathematical model, you could go through the route of using the laws that govern the system, right, as I just mentioned, or you could do it via experimental results, all right, so by experimental results. Now, when we speak about experimental results, what we're talking about is like we take the system and we would note the input and also note the output and try to develop a relationship. It's a mathematical relationship now between the two. So it's not a vague or a new concept. All right, you can take a system like a black box, you don't know what is inside of it, and you could apply inputs to the system and note the output. And from that, you could derive some mathematical equation to describe what is inside of that box. And so that's called experimental approach. Now, the motivation for mathematical modeling comes from the benefits to be derived from this approach. Now, mathematical modeling allows engineers to design and carry out computer simulations of some very, very complex systems, right? And it allows the engineer to do this without spending money on implementing models. So if someone is going to develop a new jet engine with the use of models, the engineer can design this engine or create designs of the engine and test them on the computer without placing purchase of a single bolt or component. All right, so you can see from that with computer simulations, you all use a computer. Yes, you need a desk, you need a computer, right? And you can go ahead and do, of course, with the appropriate software. And you can go ahead and design and test complex systems. And outside of that, you'd have to know design your model, of course, maybe using other methods, maybe non-simulation methods. But what you would have to do, as would have been done in earlier times, is to actually go ahead and go and test it. And that is very costly and can also be very dangerous. All right, so computer simulation amounts to huge savings and turnaround time for development. And perhaps you can closely associate simulation with the software that you use on campus. We used to call it electronic workbench. It's now called, name just slipped me, but it's National Instrument software for simulating circuits. So you would take out your components and you can design any circuit that you are interested in, and you can simulate it right there and then, okay, without going to the store to purchase any electronic component. So just highlighting the benefit of mathematical modeling. You may ask the question, where is the mathematical modeling? In the software that you use to do your electrical circuit simulation, each of those components that you pull out, there's a mathematical relationship or a mathematical model that is in the background that you're not exposed to, okay? But it is in the background, and once you pull that component out, that model will follow through and begin to add in the system to create a much more complex model, all right? Just to bring into context the whole issue of mathematical modeling. Now, mathematical models are derived mainly through, as I said before, experimental studies or from theoretical principles. Models are not perfect, that must be understood. They have their limitations. So you can develop a model, but it will never ever come to the point where it's exactly the same as the physical system. However, I must add that models can be created with sufficient accuracy that the systems can be equated without noticing any difference between the two systems' performance. Okay. Common types of models, we have the differential equation type model, we have the difference equation, which is used for discrete systems, digital systems. We have the transfer function, And we also have the state space model. All right, so these are models that can be used in representing systems. We're now going to turn our attention to the transfer function model. So the transfer function of a linear time invariant differential equation, and we abbreviate that LTI. So LTI system is defined as the ratio of the Laplace transform of the output, all right, output response to the Laplace transform of the input, all right. And this is done with all initial conditions at 0. So let us go ahead and consider LTI system defined by, I'm not seeing my equation, so put that equation right here. Well, all right, let's see what's happening. When I upload the file to Blackboard, apparently some of the formatting got removed, as I'm not seeing my equation here. So what I'm going to do, all right, all right, I'm going to, this is not so critical at the moment. So the PDF version of the file will have the equation. So I'm asking that you just refer to that. But what we have here is this general expression for a differential order, a differential equation, all right? Or we could say the differential equation represents an LTI system. And what I should, yes, go ahead.
So you have some persons having trouble joining the class now, sir.
And I'm not sure what did it indicate. Let me just pause the recording for a minute. I don't want to press stop. All right, never mind. Go ahead. Just quickly share what they perceive the problem to be.
Sir, when they go on the Blackboard, collaborate, sir, and then the part that says join session, and they click on the down arrow, they only see the course room link and not lecture 2 mathematical modeling, sir.
But that's what you saw when you went on, wasn't it?
Well, I see both the links, sir, and I click on this one and join the session, but some persons are only seeing the course room link only and cannot join this session.
I'm really sorry, but I'm not sure why that's happening. I'm not sure why this is happening. I'm not able to fix it right now, as you can imagine. But thanks for sharing that, which even makes it more important that I have the presentations as clear as possible in terms of the slides. All right, thanks for that again.
Yes,
I'm
sir.
going to attempt to bring up the original slide and see if I can get it to share screen on that. So let's go to home. I'm going to do that just now. So what happened when I use this format for the presentation, I'm not able generally to see when you have your hands raised, all right, or to see what's happening with the participants. But I'm going to go that route because an equation is missing from this slide. So I'm going to now try to revert to that slide. So I'm going to stop sharing now. So right. I'm going to share application screen. See. Okay, this comes up here. Not that one. All right, so you should be able to see. Are you seeing my PowerPoint slide at the moment? Are you seeing the slide now?
Yes, sir.
All right, thank you.
Yes, sir.
So, good. So this is the equation I'm referring to here. This is the equation, and this is the general equation for a LTI system. And this is the differential equation I'm talking about now, where y to the n is the n derivative of y. Okay. Same for x to the n. Now, note this expression, all right? Of course, here that y is the output and x is the input. A and b, these are constants. This is a general expression for a differential equation, right? Now, to derive the transfer function of this LTI system represented in the differential equation form, what we do is to take the Laplace transform of the output function and divide it by the Laplace transform of the input function, again with zero initial condition. What we end up with is this expression here. All right? This is the transfer function for that general expression that we looked at. Now, the important thing to remember here, and I would suppose you'd have done Laplace transform in math before, but if not, the presentation I'll be using today will cover the very basics that is needed to derive the systems that are of interest. So what the Laplace transform does is to move a function from the time domain into the S domain, where the S domain is a complex variable, right? So from time domain to frequency domain, in other words, all right? It's a complex variable S, all right? Which is having to do with frequency. Okay, so from time domain to frequency. Now, when we have a Laplace transfer function, the function is a function of S. And so if you look at the block diagram representation here, what you would see is that the system is represented by a function g of s. The input is represented by a function x of s, and the output a function y of s. So it's a function of s, and hence the transfer function would be g of s equal output, and it has to be in the Laplace form, divided by the input, again in the Laplace form. And so that expression there describes as also up here the transfer function of a system. Now, before we get into further details of the Laplace transform and how we use it, I want to bring your attention to test input signals. So remember that the whole purpose of deriving models as it relates to control system is that we can now perform simulations. That's a big motivation, it's a big plus or a big part of doing mathematical modeling, that we can test our simulations, right? Now, in doing tests of systems, we have to apply some input. And for the test to be valid, the input or the test signal needs to mimic as close as possible the signal that you actually experience in reality. All right. Now, what I'm going to present here are three of the most commonly used test input signals. All right. Three of the most commonly used test input signals. Now, this includes the step, ramp, and the impulse signals. And we're going to now look at what these look like. So the step that we I spoke of earlier, is defined here, and we call it a unit step. all right, because of the level at which this step goes. I'm ready to mute your mics, please. Please remember to mute your mics. I'm getting a feedback. The unit step input is used to mimic a sudden and sustained input, right? A sudden and sustained input. So before we get into the math of it, we could consider moving the gas pedal in a car from its initial position to some new position. And here we are doing it really quick, all right? So it's moving from initial position to some new position. Now the time domain expression for this function, u of t, is such that u of t is equal to 1 when t is greater than 0, and u of t is equal to 0 when t is less than 0. And this is defined on the function shown here. Now, you will recognize that this is a non-continuous or discontinuous function, okay? And you should recognize that the expression does in fact define the system here. All right, so t equals 0 is undefined, so to speak, okay? Now, when we take the Laplace transform of the time domain function, yes, what we end up with is a new function, u of s. And here we use capital U to represent this new function. U of s is now the Laplace representation of our unit step input signal. All right, and so the unit step is represented as 1 over s in the frequency domain. All right, so that's the unit step input signal. Let's now look at the ramp input. The ramp input is used to mimic a linearly increasing input, and again is defined as the function here. But before we get to the definition of our mathematical definition, let us try to imagine or appreciate this this ramp input. If we should go back to the same gas pedal situation, a ramp would mimic a gradual depression or gradual pressing or movement of the gas pedal from its initial position, yes, and it continues to be adjusted with a linear rate, and that would sort of mimic that situation as an input, okay? So in simple terms, the ramp is a constantly changing input, right? Constantly changing. So the gradient of this change, or the gradient of the plot that represents this change, is constant. Now let's come to the time domain function. F of t is equal to at. And if you know, or if you recall your expressions for a linear system or a linear equation, you know that a is the gradient, all right? And in this case, the y-intercept is c. So this is the plot for ramp input, ramp input, and it's defined for t greater than 0. Now, when we take the Laplace of the time domain function, what we now end up with is a new function called a over s squared, where a represents the gradient of the slope. All right, so this is the Laplace representation of this time domain function, represents the ramp. In the case of a unit ramp, all right, unit ramp, the slope would have a gradient of 1. Okay. Now the third input signal is the impulse, and the impulse input is used to mimic a shock, right? A shock. And if we think of what happened when a hammer hits a nail, it's a very sudden and a very sudden reaction and a very high impact reaction. Okay, so I deliberately did not use the impulse response with the example I gave before, so the car gas pedal, because of the limitations perhaps with the input. The input that we were looking at earlier was the position of the pedal, but here we're speaking about maybe a force, right? The force that is applied when a hammer hits a nail, of course, when you're really driving the nail in, it occurs for a very short time and it has a very high value. You could also consider what takes place when there is a collision. There's a high exchange of energy, and it's usually, depending on the type of accident, really, it takes place over a very short time. Okay, so if a car or if some object or some cart runs into a solid concrete wall, that cart will come to rest in a very short time due to the high and sudden force that acts upon it due to hitting into that concrete wall. So the examples that I gave just now would describe some examples of what an impulse input would be like. Okay, so let's look at the mathematical expression here. Now we're seeing an arrow going up, which means it is going towards infinity. The truth is, what is happening here is that we have a function that has very short duration. If you look at what is happening in the expression here, all right, we have ut minus u of t minus t, and if t is approaching 0, it indicates that u of t minus t is approaching u of t, which suggests to us that it's approaching 0. All right, it's approaching 0. The actual width, of this if you look at what is happening, it's approaching 0. So the width here is approaching, it's approaching 0. It's getting narrow. However, the limit of this part, 1 over t, is approaching infinity, because as t gets smaller, as t approaches 0, this here approaches infinity. So here we're seeing the amplitude approaching infinity, and the width, which is described by here, is approaching 0. It's getting narrow. Okay, that's the impulse. Very high amplitude, very short duration. Now the impulse input is described by this function over here. All right, that's the impulse, and so the Laplace representation for the impulse is simply 1. Right, simply 1. So this is just showing the transform equation, and the result is 1. Here are some common Laplace transform. So the first 3, we have looked at them just now. We just looked at the impulse and said that is given the transformation of the impulse, what we end up with is 1 in the Laplace domain or the frequency domain. For the unit step, it's 1 over s, and for the unit ramp, I explained that a would equal to 1. We have 1 over s squared. Right, and these are some other transforms which we're not going to look at the moment. In the case that you need other transform relation, the table we provided. Okay. Now let's look at an application of the Laplace transform. The Laplace transform must be seen as a tool. Right? It must be seen as a tool. In fact, a tool. And a tool is something that we use to make work lighter. So don't be stressed into looking at the Laplace transform as being something coming to stress you. The Laplace transform is in fact a very powerful tool. What it actually does, it allows you to derive solutions for complex systems that would have been otherwise very difficult to solve in the time domain. So you will take it over to the S domain, do your mathematical gymnastics, and then you can now come back into the time domain with a solution. It's almost like if it is that you're not able to manufacture something in your country due to whatever reasons, and you're able to take it somewhere else, and you're able now to manufacture that part or that good, produce that good with very, very, very relatively good ease, and they take it back to the country which you intend for it to be used. It's a similar thing. Laplace transform takes a complex function that you're trying to solve into a new domain. You can now use some simple methods and then get back into time domain. So let us see how we can apply the Laplace transform to a system. So the aim here is to solve a differential equation that describes the system. All right. Now let us look at the steps that we're going to apply in deriving the Laplace transform of the system. First, we're going to take the Laplace transform of the differential equation that describes the system. That's the first step. All right. So we now have that differential equation. What we're going to do is to take the Laplace transform of that equation. Secondly, we're then going to apply the desired input, right, into the equation and then derive the inverse Laplace. So what we're actually doing here is to determine what the output of the system is going to be. Okay, we're deriving or we're trying to determine what the output of a system is going to be for a given input. But instead of applying that input to our differential equation in time domain, of course, we are going to take this function from time domain into frequency domain, which by use of the Laplace transform, and then we're going to create our operation, which we're going to apply our input, and then we're going to take it back into time domain. So these two steps are exactly doing that. Here's an example. We're going to perform steps that will derive, first of all, the mathematical, the transfer function, I beg your pardon. We're going to write the transfer function for this RC circuit, right? It's RC, as you know, because it has a resistor and a capacitor, right? What we're going to eventually do is to determine what the output of this circuit is going to be when the switch is closed, all right? But the first step is to derive the differential equation that will describe the system. Now, because our system is an electrical system, we are going from first principle, by the way. Hence, we are going to apply laws that govern electrical circuits. And here we're talking about Kirchhoff's law. Kirchhoff has two laws: current law, voltage law, Ohm's law, and such the like. Okay. Now, from Kirchhoff's law, we can agree, and if I go back to the previous slide so that we can appreciate what is going on, if we apply Kirchhoff's law to a series circuit, what Kirchhoff's law says is that the sum of the voltage drop around a loop must be equal to 0. So in other words, we could say that Vs of t, right, plus Vr of t. And by the way, we have to, when we're doing Kirchhoff's law, we have to be careful in terms of how we write down these expressions. I would expect that you would have been putting things like this on your net, on your system, all right? And this will be positive here and negative. And if we're going in this direction, okay? If we're going in this direction, so let me cross this out. And so we're starting here, and if we could, whenever we meet up on, and I'm not sure what method you have been using, but you can come in and let me know if it's any different. If we start, you could choose anywhere you want to start, really speaking, you could choose anywhere, okay? If I choose to start here, then I meet upon Vs first, and so Vs, because I'm going towards a negative polarity, I am going to put positive, so it's Vs of t, all right? And I'm going around. Next component is my resistance. I meet upon a positive first, and so I'm going to put minus Vr of t. Continue to go around. Again, I go to my capacitor and I meet upon the positive first, so it becomes minus Vc of t. Of course, I'm using Vr to represent the voltage drop across the resistor, Vc the voltage drop across the capacitor, okay, and Vs, of course, is the supply voltage. When we add all of these voltage drop, according to Kirchhoff voltage law, it should be equal to 0. All right, so that is one law that governs a part of this circuit. Okay, so we have Vs minus Vr. I'm sorry, Vs minus, that's correct, Vs minus Vr minus Vc equal to 0. That is a law that governs the circuit. We know for sure, based on what we have understood in science, that yes, this law defines or describes voltage drop across the circuit. Now, it is important, I did not point this out earlier, but it's important to understand that when we're deriving a transfer function, right, it's important for us to know what the inputs and output, in fact, the inputs, sorry, because you could have more than one input, but for our purposes in this module, we'll be only deriving models for single input, single output systems. Okay, so the point I'm making right now is that whenever you're deriving a model, you need to know what the input and the output are. Okay, all right, so this is one word, output. Pardon the error there. So we need to know what that is. And here we're given that the input is the supply voltage Vs, and the output is the capacitor voltage Vc. Okay, that's important. Now, to go to the next slide, we are now going to continue looking at the equations that describe the system. So here we have the first equation being Kirchhoff's voltage law, just written in a different form. It's the same expression. And what we really want at the end of the day is to have a transfer function that is of this nature. Output Vc of S over the input, which is Vs of S. All right, remember the output is the capacitor voltage and the input is the source voltage. And so remember, when we take the Laplace of these two and divide them or find the ratio, it will look like this. Okay, now our task at this moment is to derive or to come up with a differential equation that has only two variables. Yes, only two variables in it, and these two variables must be the input and the output variable. Okay, only two variables. So now when we derive the very first expression, let's see if we could stop there. Let's look at the variables to determine that. Here we're seeing three variables: Vs, Vc, and a third variable, Vr of t. All right, so Vs of t, Vc of t, and a third variable, Vr of t. Now, as I said before, we only need two variables. We have to, for us to get it to this point, only two variables. Need to be in the expression, and so this variable is not one of them. So what do? We have to replace that variable with an expression that is written in terms of Vs and Vc, or either. Okay, so the question now arises: what do we know about Vr? And I'm speaking mathematically or equation wise. Okay, we could say that Vr is equal to IR. All right, have it right here. All right, Vr is equal to IR. So if we went ahead and substitute IR in equation 1, we would still have a challenge. All right, what would be the challenge? Can somebody open your mic and just share what would be the challenge based on what our objective is in deriving the model?
We don't know IR would be another unknown variable.
Well, don't close your mic as yet. Remember, these variables now are all, in the way you put it, unknown. But the objective that we're seeking here is to have how many variables in our expression? How many variables in our differential equation?
2.
2. And what are those 2 variables?
BS and BC.
Correct. And so any other variable apart from those 2 you just mentioned would have to be what?
Replaced with
Correct.
expression that is similar
Replaced with VC or a function of VC or BC and VS. That's correct. So here it is now that we have I of t times R, yes, being placed here. The question is, what is the variable that we need to now replace?
I of t.
I of t, correct. Correct. So the question now arises, what is it that we know about I of t? And so this equation now would come in handy, right? It's a series circuit. Thank you very much. You can go ahead and mute your mic. Thanks for contributing. So here it is that we have a series circuit. All right, let me go back to that slide. It's a series circuit. So whatever current is passing through the resistor is also passing through the capacitor. And so what we now have is an expression, yes, so equation 2 is deriving a current. And the current that is passing through the capacitor, the equation reads I of t, it actually could be IC, it's the same as IT, okay, it's the same current. But strictly speaking, the capacitor current is equal to the capacitor value times the rate of change or the first derivative of the capacitor voltage respect to time. Okay, C times dV C of t dt. Now look carefully at the expression for I. The variable in that expression is VC, which satisfies our requirement. Therefore, we can go ahead and substitute for I of t in this expression, which will then place in the first expression. What it comes down to be is this, all right? So I of t is equal to, make sure I have this right now, is equal to, let's look at this carefully. This should be.
Yeah, go fix the side for it.
If there's a need for it, it will be done. Hello?
Oh, alright, fix this.
Yes.
Yes, sir. I think the expression is I of t is equal to the product of RC times d of VCT all over dt. So the slash dt is supposed to be in the denominator.
Are you talking about equation 4?
That's correct, yes, sir.
It should be in the denominator, isn't it? In the denominator, d of t is in the denominator, the slash there.
Right. But I think that was the issue with it.
All right, what should be here is this, VR, all right? VR.
Oh.
Yes, VR. What we're doing here is to substitute. So I times R, remember that I is this part here, all right? Let me go ahead and do this now so that when I upload, I just do one.
I, sir, IT, sir.
Sorry, go ahead.
So I'm saying I'm correcting not I, but IT.
You're talking about IFT, that is where now?
No, as in the part that is just circle, sir.
Oh, okay. Okay.
So I'm saying I respect it.
I understand. Thank you. So it is not going to be I of t, but it's going to be what? VR of t. All right. VR of t. Okay. So I'm going to attempt to adjust this here as we speak. So I'm gonna do this now before I forget. Font having a try this. I suddenly forget where my subscript is. It's a little bit different in PowerPoint.
Check the size.
Sorry, let me just leave it at this for now. All right. All right. Let me just do this. I think this should work just as well. All right. So, right. So let's come back now to. So I hope persons would have seen the situation here just now. All right. So we can proceed. All right. So VRT, what we're actually doing here is to substitute the value for, the description or the equation for I in the expression here. So it becomes R times C dVc of t dt. And then we can now substitute this expression 4 in equation 1. And what we're going to be ending up with now is this expression. All right. Now, when we take a look at the expression, what we recognize is that there are two variables, V of C, or should I say Vc of t, and Vs of t. And hence it would satisfy what we set out for in the first place. Having gotten this, we can now proceed with the next step, which is to take the Laplace transform. Okay. Now, let me come back to the previous slide and ask you how we will treat this. You have to remember the fundamental rules of the Laplace transform. And I'm going to go over here and just do it in summary for maybe persons who may not call or may not have done the Laplace transform. So we take the Laplace transform of a function, for example, f of s. When we take the Laplace transform, what we simply get is v, change the letter k, the size of the letter for the function, make it a capital letter for just showing that there's a difference. It becomes vs of s. Yes, simple. So if let me forget for a while, not using v of s, but any function. So let's say we have a function of t, because I had something wrong here a while ago. All right, so let's listen again. If there's a function f of t, right? So f is a function of t, and we take the Laplace transform, what we end up with is a new function called f of s. And notice I put capital F this time. Now, if we take the Laplace of a function of t, which is of its first derivative, using the symbol to represent the first derivative of the function f of t, when we take the Laplace of that function, what we end up with is s times f of s. These are the rules of the Laplace transform. So persons who are not remembering it or not familiar with it, we just need to go to any website or any textbook on controls to look at the fundamental Laplace transforms. So with the same breath, the Laplace transform of the second derivative of f of t would be what? Can somebody share what that would be, please?
S squared f of s.
It would be s squared f of s. That is correct. And so the Laplace of, don't close your mic as yet, f to the n derivative, or the n derivative of f of t, when it take the Laplace, it becomes what?
S to the n f of s.
Correct. All right. Thank you. Now the third type of function that we may end up looking at is the integral of f of t. Yes, what do we do when we take the Laplace of the integral of f of t? What is going to happen? What happens is that we end up with 1 over s f of s. All right, thank you very much. So that would be the general rules for the Laplace transform, which you would need to know. Okay. So what we're seeing here is that when we take the Laplace of the function that we had on the previous slide, what we end up with is f of s, sorry, fs, f subscript s of s is equal to r times c times s times bc of s plus bc of s. All right. And what we will do next in the next line is to simplify. So what we could do here is to factor out the VC of S, and when we end up with this. All right, end up with RC times S plus 1 all times VC of S. And of course, remember, transfer function is output over input written in the Laplace format. Can you remind me which of these two variables, yes, is the input?
VS of S, sir.
All right, so this is the input. And transfer function states that what must happen? Output over input, which implies that for this one, we're now going to put what? VC of S over, it's actually written right here.
VS of S.
Right, so that is why it looks like this. And this now is the transfer function for the RC circuit that we looked at in a few slides back. All right, so any questions on the steps just looked at?
Sir.
Yes, go ahead.
So the Laplace transform takes things from the time domain to the frequency domain?
To a frequency, yes. So S is a complex variable that, well, it's frequency domain, and S is a complex variable.
I think I watched a video today that said the Fourier transform does the same thing, if I recall correctly. What is that, like, what's the difference, or is there a time when you should use one or the other?
All right, I don't want to discuss the Fourier transform. I don't know what the mathematical background is for other persons in the group. I know that you would have, well, you should have done engineering maths 1 and 2. But what I want to appreciate at this moment is that there is a transform. There are a number of other different transform in math. But what we're looking at right now is called the Laplace transform. Simply put, it converts a time domain function to a frequency domain function, a function of S, where S is a complex variable. So for now, try and appreciate that fundamental, and then you could now look at what the Fourier transform is and make comparison. But you shouldn't proceed to make comparison until you fully appreciate what each of them is doing. So for now, just appreciate that the Laplace transform is taking a time domain function into frequency domain, and we're using the Laplace transform to assist us in deriving the output of systems, all right, given the input. So we're going to apply our input in the frequency domain, and then take that new function back into time domain to see exactly what it is. And we're going to do that in the next couple of slides. Okay? Yeah. So right now we must appreciate that this, or agree that this is the transfer function. I'm sorry, specifically speaking, yes, that's the transfer function for our RC network. All right, so I'm putting it here for us to see it again. Here's a block. So we have this block, and in that block we have an expression, and the expression is describing the relationship between the input and the output. But again, here we're speaking of the transfer function, and so transfer function, the expression is going to be a function of S. Now let us see how Laplace transform really works. So we're going to determine the time domain expression for the output signal Vc of t. We want to know what it is that the capacitor voltage will look like when the switch is closed. Now, you remember me discussing with you earlier some standard input signals. We looked at 3. Now, when the switch is closed, what do you believe would be the signal that best represent a switch being closed? Would it be a step? Would it be a ramp? Would it be an impulse?
Step.
All right,
Impulse.
so a step. All right, so I hear step and I hear impulse. Would you consider the closing of that switch to provide so what happened, let me I'm going to go back to the slide a little bit to show you what's going to happen. So here we are. The closing of that switch here is providing a signal that is equal to, in fact, you should say this is actually 1 volt. All right, whatever it is, if it's even 10 volts, it doesn't matter. But what will happen is that before you had 0, and then you now suddenly have what? A finite finite voltage value. Do you agree?
Yes, sir.
Right, so you have some finite, we're going to call it V. It doesn't matter what V is in terms of its size, but it's finite. Well, what's the difference between that V and, theoretically speaking, the impulse? What would be the difference? Can you identify the difference? So when the switch is closed, do you think? Go ahead, please. Yes, go ahead. What's the difference?
The area underneath.
Sorry, go again, please.
The area underneath the curve. Is
What
it one?
about it?
It's not 1. It has to be 1 for it to be an impulse.
For which one that is now? This one?
Yeah, it's not 1 for that one, but it's
All right. So mathematically speaking, you're saying for it to be an impulse, the area on it should be 1. But let us take our attention from the plots and try to appreciate what is happening to our circuit when the switch is closed. Do you presume that you'll have a function that looks like this or a function that looks like this? Note carefully that what this is speaking about is the voltage entering the system. Okay, will the voltage signal look like this here, or will it look like this, where it goes up to a very, very high value, almost infinity, and comes back down after a very, very short time? Which one do you say?
So it will be the step function, sir.
So it will be A, the step, because the voltage remains the same once the switch is closed. Do you agree? It's a DC source. Are we agreeing on that?
Yes.
Good. So it wouldn't be the impulse, because the impulse has a very high amplitude and only lasts for a very short time. And so this switch here would not be doing what is happening here. All right, just to appreciate how we select, or why we selected to use the unit step. All right, and I say unit step here because the actual amplitude of our signal is 1 volt. All right, so the task at hand is to determine the time domain expression, yes, for the signal VC of t, and VC of t was the output that we derived for, well, sorry, it was considered to be the output in deriving the transfer function that we looked at in the previous slides. Okay, so now the step that we're going to take is that we need to know that 1 volt, yes, will represent a unit step. You can go ahead and mute your mics, please. Thank you. And this will be represented by the function Vs. Vc of s equal 1 over s. And you recall that 1 over s is the Laplace representation for the unit step. Now, please remember this. Transfer function is equal to output over input. Therefore, what is the output? Transpose. Go ahead, please. It's equal to transfer function times input. That's how simple it gets in the S domain. Just simply multiply the transfer function by the input. And so we have done that right here. The next move now is to take this function where? Into the time domain. That will be our next task, okay? So now there are different methods that you can apply to taking this function back into time domain. I mean, here I should say different ways of simplifying the expression so it can look like what we have. So if we were to remember this expression, it's 1 over CRS plus 1 times S, all right? And we're going to go back to that table that I showed you earlier. So we have 1 over S times CRS plus 1. That's the function that we wish to take back to time domain. Can you look at this expression here, or the expressions here, and tell me which one would perhaps best look like what we are working with? Which of them? If you're going to open your minds, which expression we have in this table best represents this one here, and why?
Sir, 6.
6, sir.
1 minus e to the 8.
All right, I'm hearing 6. I'm hearing 6, and I could ask you why, but I'm going to save some time because we have a couple of grounds to couple of things to cover. So for you to actually say that this is looking like this, we have to have it in the same format. Firstly, note that the coefficient of S in here is what? What's the coefficient?
1.
1.
1.
We have to do is have a factor out CR. Then they probably
That's correct. So to make the functions equivalent in terms of how they look, yes, we have to make the coefficient of S in our expression equal to 1. And how we have to divide throughout by what? CR. So we're going to divide the numerator by CR, and we're also going to divide the denominator by CR. So we're going to end up with what here? So now S plus 1 over CR. Do you agree with that? Do you agree?
Yes, sir.
Good. And now we can say, yes, it is now looking like this expression here. And we can clearly see that A is equal to what? 1 over CR. Okay, and so you see there, it's not difficult to manipulate your way in terms of adjusting a function. We're not modifying the function, we're just simply putting it in a form that is going to make it appropriate for comparison. So we're not adjusting it. We have not adjusted the expression. I hope we're seeing that. I am not adjusting the structure. This is equivalent. I need to point that out. It's equivalent, and I hope that person sees this. All right, this is just math here. And so we can set A is equal to 1 over CR. So if we substitute based on what we see here, then the solution would be what? C of t equal 1 minus e to the minus 1 over CR, and that's going to be times t, so we just put t over CR. All right, so that would be what the inverse Laplace would present us with. Now I'm going to go back to the slide that we were looking at earlier. So we did a little bit of a different approach here, where we did partial fraction, but this is not necessary. If you have an easier way to do it, that's fine. This is doing the whole partial fraction situation. But we went ahead a while ago and did a very simple procedure, and we ended up with the same solution. I hope you've seen that. So what we have just seen here is that the time domain expression for the capacitor voltage is 1 minus e to the t over CR. Now let us prove to see what exactly is happening with this solution that we just derived. Let us apply mathematical principle for sketching a function. All right. And of course, this is time, and this is the capacitor voltage, respect to time, capacitor voltage. sorry, let's put VC, capacitor voltage in volts. That's the correct label for that axis. And so, what is the output of the function when t is equal to 0? Can somebody tell me what is VC when t is equal to 0?
1.
1.
1, sir.
It's equal to 1. All right, so I hear 2 persons saying 1.
0, sir.
And I hear 2 persons saying 1 and 1 person saying 0. So what do I write? All right, let's break it down. Let's take e to the minus 0. What is e to the minus 0 equal to?
1.
It's equal to
1,
1.
sir.
Persons who are not aware of this need to go and check the principles of exponentials, particularly e. All right, so e raised to the 0 is equal to 1. All right, and so we end up with 1 minus 1, hence 0. So BC, I'm going to try to put it here, BC of 0 is equal to 0. All right, so we know that the function is going to start here. Okay, now the question is, what happens to the function when t approaches infinity? What happens to the function when t approaches infinity? All right, what happens to VC of t when t approaches infinity? So again, oops, let's get this back here.
So will the function approach 1?
Function will in fact approach 1. And so what is happening here is that there is some asymptotic relationship taking place. The function never gets past 1. Do we agree with that? It never gets past 1.
Yes,
so as
sir.
t gets larger, it never gets past 1. And now if we look at the general behavior of this function, it is behaving, you know what the function e of t behaves like? E raised to the power of e to the t. It's a curve. Let's call it a growing curve. So it is going to, it's going to look like this. It's growing, so it's going to start out like this. All right, and begin to move across. All right, now I could do other intermediate steps, but for the interest of time, I'll stop here. But what do we recognize here? We're now seeing a sketch of the capacitor voltage when the switch is closed. Does this ring a bell? Does the plot looks familiar?
Yes, sir. That's the charging curve for the voltage of the capacitor, sir.
For the capacitor, that's correct. And so here it is that we have used the Laplace transform. Well, of course, we derived a differential equation for the circuit, use the Laplace transform to carry it into the frequency domain, applied our input, and then now come back to time domain, and we're able to have an expression, yes, that describes the behavior of our network. And we have just proven that by sketching the function that we have here, the time domain function. And so this should be sufficient proof of, at least initially, at some basic level, that the Laplace function is in fact a tool, or the Laplace transform is a tool that is very useful in control system engineering, particularly for the reason that we're able to derive a transfer function that we can use to determine the time domain expression for the output. All right. Any questions on this before we move to the next section? All right. Let's now take a look at the permanent magnet DC motor. The motor is a commonly used device in control systems. You think about robotics, you think about servo systems. We're talking about the use of motors, but let us now look at the permanent magnet DC motor. So the structure of it, we have the rotor, or we call it armature, and this is a coil that is wrapped around an iron core. And we have in the casing, or attached to the casing that surrounds this armature, we have permanent magnets, all right? Permanent magnets, right? To provide the magnetic field. Of course, we have the brush commutator that distributes the windings to the brush, and so on. We're now going to look at the steps in deriving a mathematical model for this permanent magnet DC motor. So the task here is to derive a transfer function relating the angular speed, which we'll call omega s, because we're speaking now of the Laplace version of it, to the applied input v of s. So this right here is a representation of the motor, but we're looking at it in terms of transfer function. Remember, transfer function is a function of s. That is why we have v of s and omega of s, where v of s is the supply voltage and omega of s is the angular speed. Now, let us look at the structure of the DC, of the permanent magnet DC motor. And we're looking at it in terms of electrical system, because there are two parts. You need to recognize that the permanent magnet DC motor has an electrical part to it. It's an electromechanical device. I don't know if you've heard that term before. It's an electromechanical device. It's electrical component to it, and there's also a mechanical component to it. Now, for the electrical component, we could represent it as such, all right, where EA of T is our supply voltage to that motor, R is the resistance of the armature, L is the inductance of the armature, and we have the symbol for the armature, but just to indicate that we have what we call a back EMF, right? The back EMF that is produced in there, okay? So that's a back EMF signal, so to speak. On the mechanical aspect, we are seeing a mass that has a inertia represented by J, and we say inertia because we're not speaking about translatory mass. So if mass was going along a straight line, then we consider mass, right? However, if the mass is going to now be, the object is now going to be rotated about some central point, or some point for that matter, then we no longer consider the phenomena of mass, but inertia, which has to do with mass, but not strictly speaking in terms of mass. So inertia is a function of mass, okay? But it speaks to objects that are rotating, right? In addition to that, we have to consider torque on that body, and we also look at the angular speed of that body. So there is a list of variables associated with the DC motor, and it might seem like a long list, but if you just take it step by step, you recognize that yes, everything is accounted for. So electrically speaking, we will start here. Well, let us not be that way. Let us start electrically though. We have the armature voltage, which we discussed earlier, armature voltage, which essentially in our case, we are going to see what I used before. I use EA, all right, fine, no problem. The supply voltage, we have EB, the back EMF, we have IA, the armature current, RA, armature resistance, LA, armature inductance, JM, the term for this, which is the load moment of inertia, yes. Omega M is the angular velocity of the motor shaft. BM, frictional load. T of T, torque. And these are some constants now. So the reason for me actually putting these expression is to show what are variables. So everything that is a function of time is a variable. These are constants. All right, those are constants. This is not a constant, sorry. Let's clean that up. All right. So this is a constant. This is a constant again here. Constant. Okay. All right. So those are constants. So torque constant, back EMF constant. These are terms associated with the operation of the system. Now let us first of all look at the electrical laws. Again, Kirchhoff law will play a dominant role, and it's always a good place to start. This, of course, is Kirchhoff's law, right? Where we are adding algebraically the voltage drop across the electrical network. So we have the source voltage represented here. This is the voltage drop across the inductive component. This is the voltage drop across the resistive component. And of course, this is the back EMF. Okay. Now, this expression here is just showing the relationship between the back EMF and the speed of the shaft. Of course, the faster the shaft rotates, the greater the back EMF. And hence, we have our back EMF constant. Right? Now, I want us to recall that whenever we are deriving a transfer function, we need to have only two variables in our differential equation. That is necessary. Okay, that is necessary. So even though we have multiple variables here, at the end of the day, we have to replace the ones that are not required to express them in terms of what is required. So let's continue. Let's go to the mechanical aspect now. And again, mechanical laws will apply. And we have Newton's law, all right, being applied here. So the torque that is produced by the passing of the current through this network is proportional to the current that we apply through this system. All right. Now, when we speak of Newton's law, we could also speak of the force. So we could say the torque is proportional to what is equivalent to the mass, the inertia, times the rotational acceleration, mass times acceleration, right? And this is the force due to friction, right? Frictional constant, the faster you rotate this thing is the greater the frictional force, okay? And so the constant of proportionality is Bm, where Bm is the frictional constant. The faster the shaft rotates, the bearings are going to be experiencing a greater force. So the difference here, when we add these forces, of course, they're going to be in different direction. That will give you the resultant torque. Okay. So by means of substituting where necessary to remove or to replace rather the variables that are not required, this is what we're basically doing. So if you follow through the steps here, we see that we're replacing we're replacing expressions that need to be replaced. So remember, the two terms that we need in this expression, they are what? The supply voltage, and we need the speed. So in terms of the time domain, we need V of t, which is in fact we call it, I think we call it EA, if I'm not mistaken, we call that EA. All right, that's correct. So let me use the correct terms here. We use EA, all right, EA of t. I'm going to clear this up. This has to be very clear what I'm saying to you now in terms of what we need, because it's going to be the guiding factor in our simplification approach. So when we finish doing our simplification, we need to have two variables. The variables need to be EA of t, and we also need omega yes, omega m of t, which omega m here is the motor angular speed. And of course, this is in time domain. If we have a differential equation with these two variables in it only, then we can proceed to apply our Laplace transform. All right. So the steps here are the approach used to simplify the expression. Okay. So if you follow through with it, you see that we're successively removing terms that are not needed. Okay. Same thing for the we continue to do this, right, until go ahead.
I just scanned the slide before class,
Right.
and I'm wondering if that expression omega m, if it's correct. Just confirming.
And in terms of what equation you're referring to now?
I was wondering whether or not it isn't home hem. You had home hem not too long ago.
Yeah, but remember, all right, put it this way. Let me see this what you're referring to. This is symbol here with like a double. It's actually me trying to write omega.
Okay.
Capital, I'm sorry, common omega.
Okay.
When we do the Laplace transform of this, what we end up with is this.
Right.
That's understood?
Yes, sir. Thanks.
Right, good. So you could go through and look at the expression and verify its validity. But here you just see the steps in removing the verbs that are not needed. And so if you look at this expression here, we're down to here, k times t. All right, k times t times this here is supposed to be times ia of s is equal to omega m times omega m. The subscripts need to be a little bit clearer. S of s times bm times omega m of s. All right, these are subscripts. All right, these are not representing masses. Omega m. All right. Perhaps if I could go in and tie that up before I post the updated slide. All right. So any concerns about what you're seeing at this point? All right. So what we end up with when we substitute all those values is that we have the transfer function again, omega m of s over the source voltage EA of s. And this expression here is what describes the relationship between the supply voltage and the motor's angular speed. All right. This is another way of writing it. It's the same expression actually. All right, same expression. Okay, and you recognize that it's a second order differential equation. Right here, we're just simply expanding the denominator. And so we now have it in a polynomial form, right? Where you have s squared, s, and the constant, right? Everything here is now the constant. This format is more appropriate when we begin to look at simulations with a particular tool, right, called MATLAB. Okay, we're going to do derivation for one more function before we close off this presentation. We're going to look at derivation of a purely mechanical system. Electrical persons tend to be afraid of mechanical systems, and electrical students, well, mechanical students don't like to see networks. But engineers in controls need to appreciate them both, because systems don't just come purely mechanical or purely electrical, but they sometimes come, in fact, they most times come in both forms, electromechanical. All right, so here we have what we call a spring mass damper system. And it's so called because we have a system comprising of a spring, a mass, and a dashpot, right? So a damper. Now, the task at hand here is again to derive a transfer function. Question is, what is the input and the output? So the input here is the force we're going to apply. So this is the force, and the output is the displacement of the mass. All right, and it's represented here. So note, what I circled over here is the Laplace representation for the input and the output. What is shown on the diagram on this side is the time domain expression for the force and the displacement. Let us now proceed to derive the transfer function for this system. Now, we are going to take this spring mass damper system and we are going to simplify it. So we're going to draw a mass. This is what we call the free body diagram. So we take the mass and we take all the forces acting on the system. So we know that there's a spring attached to the system and we know that there is a dashpot attached to the system. And then we have a force which is going in the opposite direction to these forces, and also acceleration which is going in the direction of the force. At least we can always write it in that way, right? It will work with itself eventually. Now, we have to appreciate what each these forces are, and we need to know, are they aware of what they are mathematically speaking? How do we relate to these forces in terms of displacement? So let us take the spring for starters. What do we know about a spring and its displacement? What do we know about the force on a spring and its displacement? Please go ahead and open your mics if you would love to contribute, and I'm invited to contribute.
So the force on the spring would be directly proportional to its displacement.
All right, so that's correct. I'm going to use f of t. Let's use it like this. Thank you. So the force on a spring is directly proportional to its displacement, and that therefore implies that there's a concept of proportionality. So force on the spring is going to equal to the spring constant times x of t. All right, x of t, this is x. And hence, this is why we can now describe the force on the spring, or the force due to the spring, as equation 1. Now, the dashpot may not be familiar to you, but the dashpot is really a piston that is, let me sketch it here. Think of a piston, or I'm going to sketch something here. Think of something like this. Here is sealed somewhat, and there is maybe a couple small holes going through this. This is a cross-sectional view, and this is oil inside here. The oil can move back and forth, but what happens is that this little piston here needs to move through the oil. When you apply a force, it moves through the oil, and so there's going to be a friction, a fluid friction, right? Viscous resistance as you try to move that piston through the oil. Now, there's a principle. The faster you try to move this piston through that oil, is the greater the resistance that you're going to face. Okay. So the lighter, so you could take those who may have had the opportunity to take out the dashboard from a car and to maybe, well, let's say not take it out. If you were to lean down on the bonnet of a car, or perhaps to exert some force on the back of a pickup truck, all right, a pickup, what you recognize is that if you gently press on the back of the pickup, you will be able to move the truck, or you'll be able to see movement in the suspension or the entire chassis of the vehicle. If you should do it suddenly, you will not experience significant movement. All right, you will not. You could try this on your own, but don't press down on the bonnet of anybody's car, or yours for that matter. You will then the thing. What I'm saying to you is that if you gently press down on the suspension, you will find you're able to move it much easier than if you were to do it really fast. There's far less opposition. So the dashpot has an expression that says that the force due to the dashpot is proportional to what? The speed at which you move it, or the rate of change of its displacement. All right, this is what the expression for the dashpot looks like. It's proportional to the rate of change in displacement. Therefore, there is also a constant of proportionality which says that FD is equal to, I'm going to call that B, constant of proportionality B times dx of t. All right, that's the displacement. Hence, the dashpot force is represented by equation 2. Force by the dashpot is equal to the dashpot constant times the rate of change of displacement. All right, so that those two expressions describe the relationship between force and displacement for the two objects, the spring and the dashpot respectively. All right. Now, having written that, we can now begin to look at the interactions of these forces. Now, Newton says that the sum of forces acting on a body, yes, let me see if I could write this down. The sum of forces is equal to what? Mass times acceleration. Do you recall that? We had all the forces, bearing in mind that forces are a vector. So you have to note the direction as well as the magnitude. So when we take the sum of these forces, it is equal to the mass times the acceleration of the body. So the sum of the forces on the body is equal to the mass times the acceleration that the body will experience. And so this is written here. Now note, I'm putting mass times A, acceleration is equal to F. Now note, what is happening in my description here is that I'm calling down positive. Right? It doesn't matter what you do. You could call up positive, it doesn't matter as long as you're consistent. Okay. So acceleration is going down, so there's a positive vector. Force going down, positive vector. Fs, Fd are going up, hence negative vector. So let's add mass times acceleration positive vector is equal to force, positive vector, plus negative vector k times x of t, which is the force due to the spring. Again, negative vector, again, the dashpot force, negative b times the dx of t, all right, dx of t dt. So what we're doing is to now add the forces and equate them to the mass times acceleration. Now let's replace a, because remember, with every single model, we need to have only two variables. And in this system, we're interested in what? The force that we're applying to the system, as well as the displacement of the mass. Now, right here, we have a variable called acceleration. We have to replace that, okay? We have to replace that. But that's not difficult, because you recall that acceleration is a function of displacement. So the rate of change, or should I say, excuse me, the double derivative of displacement is acceleration. So what I have right here is the double derivative of displacement, which is acceleration. All right. So mass times the second derivative of x of t, respect to time, is equal to the sum of the forces. And now, if you examine that expression, what you recognize is that you only have two variables in the function, x of t and f of t. Didn't put t here, but it's noted, right? And from here now, we can go ahead and apply our Laplace transform. And I'm not going to go to the next slide yet. Maybe there are persons who can actually whoever printed the slide, but for the exercise, can you go ahead and tell me? We're going to now do the Laplace transform for this expression. So can you open your mics? Anybody can go ahead and open your mic and just tell me what the Laplace transform would be of this function here, please. Go ahead. So we'll put back our constant m. I'm helping you out. What would be the Laplace transform of this section right here?
S squared xs.
S squared because it's the second derivative, and you're going to put capital X because we're taking the Laplace of x of t, so it becomes x of s. Continue, please. Equal this function here now. It's a function of t. I just didn't put the t like this. So we take the Laplace transform. What will happen?
Fs.
F of s. Okay, when you say fs, just f of s. All right, fine, that's good. What about this part right here? Put back your constant, and then this is a function of t. So what would it be? Then take the Laplace.
Capital X.
Yes,
S.
that's correct. X of s. And then the last section now.
E times S, capital X of S.
It's going to be, go ahead, please.
B times S, capital X of S.
All right. Let me write that. So it's going to be minus b, capital B times S, you said?
Yes, sir.
Times X, capital S of S. And that's in fact correct. So this is now, thank you very much. This is now, for the two persons who participated just now, this would now be the Laplace transform of this differential equation, right? Now the next step would be for us to group the terms and to write the actual transfer function. So here we now need to group the terms and run out of space. I'm going to go to the next slide, and we can see that yes, this is in fact what you just mentioned. And when we factor out the terms, in fact, we need to carry, remember what we're seeking after is this, okay? Output over input. And so if we group terms, so for example, if we take these terms over the equal sign to join with this term here, we will be able to factor out x of s. And in so doing, what we'll end up with is m s squared plus x of s plus x of s times b. Let me go one more time. I'm going to actually do it quickly here just to make sure that we are on the same. Let's do it quickly. It won't take too long. What we'll end up with is that f is equal to, and this is f of s now, all right? So hope we're not getting thrown off at that. F of s is equal to m x of s times s squared plus let's do this here, plus k, do this again, k x of s plus b x of s times s. Now when we factor out x of s, and to do our let's factor the f of s, so we can take this one out here, take this one here, take this one here. Now look at what is left. What we have is for the first part is m times s squared. For this part, what we have is what? K plus, and what we have here is bs, b times s, okay? B times s, and that is equal to, of course, we're going to put the x of s on the outside, and that is equal to f of s. So when we now write the function like this, which makes x of s over f of s the subject, what we're going to end up with is this part here, and that shouldn't be too difficult for you to see, right? And that now is the transfer function for the spring-mass-damper system. All right, so here we are seeing how we can derive the transfer function for a number of systems. We look at mechanical system, electrical system, and electromechanical systems. Okay, This will now conclude this presentation on mathematical modeling part 1. In the next session, we'll continue to look at mathematical modeling, but a different aspect of it. All right. Any questions that you may have at this point?
Yes, sir.
Yes, go ahead.
You may have mentioned it at the start of the class, but I was just a few minutes late. Regarding worksheet 1, would you be going through it like you did last semester for instrumentation, or do we just direct our questions to you via email?
Oh, well, I sort of missed the first part. If you're going to do what with the worksheet?
Yes, I was wondering if you're going to go through the worksheet.
Oh, absolutely. All worksheets will be reviewed, or should I say, will go through the worksheets, not in perhaps the way that you know how I go through if you're in instrument one. I don't necessarily, I will not go through the questions one by one, but what I'll do is to feel your questions. That's the way I prefer to do it. So when we open the worksheet, if you want to go ahead and explain how you got your result or your answer, that's fine. But I would prefer that you come to the session having attempted the question, and if there are any concerns, then you can raise them and then we together work through it. So yes, that will be done.
Okay, sir.
And yeah, and I'll let you know. I might not be able to let you know in advance. Just hope that persons can attend class as often as they need, as they should. But perhaps week after next week, I'm going to be posting the test dates. All right, I'm going to be posting the test dates in a similar way I did for the instrument systems. It'll be posted in advance, so you'll not get an assessment without having 14 full days notice. Okay, 14 full days notice. So if I post them, say tonight, for argument's sake, a test will not happen until 2 weeks clear days of today. All right, just to alleviate any concerns that may arise. All right, any other questions? All right, so that said, I am going to stop the presentation. We will pick up on the second part of mathematical modeling next week. On the matter of labs, I understand that persons are not able to get on. I'm not sure how widespread this problem is, but on the matter of labs, I sent a message. Did you get that message?
Yes, sir.
All right, so
Yes, sir.
there has been, thank you. So there has been some changes to the staffing, and they are now working out the legality and the legality, but they're working out the procedures now to have that changeover. So the person who would normally do the labs is going on vacation, is on vacation, sorry. And so the person who is now sitting in or filling that post is now being briefed and prepared for sessions. So sessions will commence upon notice. I can't say for sure it will begin next week. If it is for next week, you'll be informed in due time. Because first of all, you know if it's on campus or off campus thing. Right now, in my mind, the first lab may not very well be on campus. Okay, so you'll be informed in due time. Most of the labs will be done, I would hope, remotely, which means you would not have to come on the campus. But you'll be informed as to how we're going to go forward with the labs. Okay. All right. So enjoy the rest of the night, and we will pick up next week. All right. All the best.